Suppose we have a variable force f of x that moves an object in a positive direction along the x-axis from the point A to point B. As usual, we divide the interval into subinterval and let P equal x sub I be a regular partition of the interval A to B. We choose the arbitrary point xi star that is in that small interval of xi minus 1 to x sub I to calculate the work done to move an object from point x sub I minus 1 to point x sub I. We assume the force is roughly constant over the interval and use f of x sub I star to approximate the force. Then the work done over the interval x sub I minus 1 and x sub I is given by the work done equal to f of x sub I star times the distance from x sub I to x sub I minus 1, or that is delta x. So if a variable force f of x moves an object in the positive direction along the x-axis from point A to B, then the work done on the object is given by the integral from A to B of the work function with respect to x. Now, the most common thing that we see when we talk about work done on an object is to compress or to stress a spring. So let's talk about the Hooke's law for spring. So the Hooke's law, F equal to K times X, where K is the spring constant. So keep that in mind. Let's take a look at the next example. Find the work required to compress a spring from its natural length of 1 feet to the length of 0.75 feet. If the force constant is K equal to 16 pounds per feet. So let's start with a picture. So you have a spring and this is 1 feet long. Okay. So that the next thing we want to do, so we say, well, this thing is 1 feet long. And we want to compress this so that it becomes the length of 0.75 feet. Okay. So then, since the spring layout along the x-axis, it is movable at the origin and is fixed at the end x equal 1. So then we can describe the force required to compress the spring from 0 to x with the formula that F equal to 16x. Okay. So 16 is the spring constant and x is the length of the spring. So here you can see that because we want to compress the object in the positive direction, let's draw this picture again so that you can see what happens. So since we have a force acting on the spring in this direction and is compressed the spring, this distance here is 0.75, which means this difference is 0.25. So the force acting on the spring, compressing it and pushing it so that it becomes 0.75 feet, which means the force acting on the spring for 0.25 feet. Okay, so let's take a look at the force when f of x at x equal to 0. Okay, what meant at f of 0, we have 16 times 0. At f of 0.25, this is equal to 4 pounds. So here you can see that, well, there's increasing in the force from 0 to 0.25. This meant the work done over this interval, is given by the integral from 0 to 0.25 of the force function 16x dx. So this is ax squared evaluated from 0 to 0.25, and this equal to 0.5 feet per barrel. Let's say we have a sprint have the natural length of 1 meter, a force of 20 N hold the sprint stretched at a total length of 1.8 meter. Find the force constant K. Okay, so you start with a sprint, and the sprint is 1 meter. And there's a force acting on the sprint that stretches out to 1.8 meter. And we was told that this force F is equal to 24 Newton. Let's find the sprint constant first. Well, according to Hooke's law, F is equal to K times X. X here is the distance that's been stretched, the difference of the stretch distance from the original one. So here we know that X is equal to 0.8. So it requires 24 Newton to stretch X for 0.8 meter, which means K is equal to 30 Newton per meter. The next thing is, how much work would it take to stretch the sprint to 2 meters beyond its natural length? Well, to stretch the string 2 meters beyond its natural length, first let's figure out what is the force, right? So we know that K equal to 30. This means the force acting on the sprint is given by F equal to 30 times X. So if we want to find the work done stretching from 0 to 2 meters, we calculate the integral from 0 to 2 of 30x dx. And this is 60 joules. How far will a 45 Newton force will stretch the sprint? So now we're given K and we want to find X. Well, we know that F equal to 45x. This means, we know that we know that 30, well, we know that the force is 45. So 45 equal to 30x. So then x equal 1.5 meter. So with a force of 45 Newton, the sprint will stretch to 1.5 meter. Take a look at the next example. A 5 kilogram bucket is lifted from the ground into the air by pulling in 20 meters of rope at a constant speed. Okay, so let's draw this picture. So let's say this person standing up here and he pulling onto a pulley that holding a bucket, and we're told that this distance here is 20 meters. Okay. The rope weighed 0.08 kilogram per meter. How much work was spent lifting the bucket and the rope? Okay. So there are two things happening in this problem. One thing, we have to figure out what is the force that what is the work that required to lift the bucket. And then we have to figure out what is the work that required to lift the rope as well. So let's start with the bucket first. Let's start with the bucket. So the weight of the bucket is obtained by multiplying the mass and the acceleration due to gravity. Gravity is approximate 9.8 meters per second square. So then the weight of the bucket is 9.8 times 5 kilograms, and that is 49 Newton. Now the work done lifting this bucket alone is equal to the weight of the bucket times the distance it have to get times the distance that it needed to go. So the weight of the bucket is 49 Newton. The distance, well, we have to pull at 20 meters. So it requires 980 joules to lift the bucket. Okay, so how about the rope? The weight of the rope is vary as the distance change, right? Because as you pull in the rope, the distance of the rope gets shorter because the bucket moving up. So the distance of the rope gets shorter. So the weight of the rope is vary. So the work on the rope is equal to 20 minus x. So the weight of the rope is equal 9.8 times 20 minus x. That's the distance. Times 0.08. Yeah. So then the total work that required to lift that rope is equal to the integral from 0 to 20 of 0.08 times 9.8 times 20 minus x dx. Evaluate this integral. We get 0 to 20 of 15.68 minus 0.784x dx, and this equal to 156.8 joules. So the work that's spent lifting the bucket and the rope is the total work, equal 980 joules plus 156.8 joules, and that is 1136.8 joule. Next type of problem that we're looking at is the work required to pump out the amount of water that in a tank, for example. Assume a tank in the shape of an inverted cone with a height of 12 meters and a base of radius 4. The tank is full to start with, and the water is pumped over the upper edge of the tank until the height of the water remain in the tank is 4 meters. How much work is required to pump out that amount of water? So let's go ahead and put this into a picture. Assuming we put an inverted cone onto our XY coordinate plane and have the base on the x-axis. So here's x equal to 0. And here we have this cone. And the height of this cone is 12. And the radius is 4 meters. So think about this as we are pumping the water out of the cone. The water been taken off by each layer by layer, right? The water decreasing by each layer. So then let's just say we are pumping the water out and the water level decreasing to say at this point, also at this point, for instance. So this distance of water that's been taken out, this is 12 minus x, right? The height of the cone now becomes 12 minus x. Okay. And this distance the amount of water left over is R. Let's go ahead and set up our similar triangle proportion. Then I can see that, well, then R over 12 minus x equal to 4 over 12. I can solve for R. R then equal 4 minus x over 3. That's the radius changing over time. So then the volume of each layer of water being taken out at a certain amount of time is V equal to pi times R squared, 4 minus x over 3 squared. That's the volume of each of the layer of water. Now, the weight density of water, the weight density is 62.4 pound per feet cube. We didn't give you this in the problem. However, we do need this information to calculate the force that required to take out that certain amount of water. So the density of water is given here. Now that we have the density of the water and we have the volume, the work that required, the force that required to lift out that amount of that layer, to pump out that layer of water, force then equal to the density of water times the volume. So now, well, we pump out the water so that the distance, so that the water remain in the tank is 4 meters. We pump it out so the water remain in the tank is 4 meters. What meant, since the cone is 12 meters, we pump out 8 meters of water. It makes sense, starting from x equal to 0, and we pump it out until we have 4 meter of water, height of water left in the cone would mean we pump out 8 meter. So then the work that required to pump out 8 meters of water from that inverted cone is the integral from 0 to 8 of the work done, of the force. 4 pi times x times 4 minus x over 3 dx. Evaluate this, we have the work done is approximate 33,456.7 joules.